والصلاة والسلام على أشرف الأنبياء والمرسلين. So please don't forget to make the attendance online. So I will go through the greedy design strategy for just a recap for this one. Greedy design strategy. To find the ringing telephone, you would simply be to walk in the direction of the ringing of the phone until you found it. The problem here is that there may be a wall or an expensive and fragile vase between you and the phone, preventing you from finding it. So here, greedy technique is construct solution for optimization. So it's not only find solution but optimize the solution. Piece optimization program piece by piece through a sequence of choices that are feasible, locally optimal, irrevocable. For some problems, yields an optimal solution for every instance. For most, does not, but can be useful for past approximations. Application of the greedy strategy: optimal solutions, change making for normal coin denominations. So here we'll add this problem. Minimum spanning tree, single source shortest path, simple scheduling problem of man codes. So here approximation, here optimal solution, and here approximations. Also approximations, traveling salesman's problem, TSP, knapsack problem, other combinatorial optimization problem. Change making problem: given unlimited amounts of coins denominated D1 greater than dm, give change for amount n with the least number of coins. Here we need change with the amount of n with least number of coins. So here we have example d1 25, d2 10, d3 5 and 1, and n is 48. So the change I want to return you back is 48. So what is the best solution to give you the change with the minimum number of coins? So here, if I say 25, 1 coin 25, 1 coin, 2 coin 10, so it will be 45, and 3 coins 1, it will be 48. Greedy solution is optimal for any amount, and normal set of denominations may not be optimal for arbitrary coins denominations. So also it is for optimization, but sometimes it will not give me the optimum solution. Change making problem, coin change problem. How can give amount of money made by the least number of coins given denominations? Example D1 20C, 10C, and D3 5C, and D4 1C. Now n is 36. So here 36 minus 20, 16. So this will give you 1 coin 20, 1 coin 10 will be 30, 1 coin 5, 35, 1 coin 1, 36. So here I will give you how many coins? 4 coins. So 1 coin from each note. So 20, 10, 5, 1, it will be 36. Look at this here. Give a limited amount of coins, denominations D1, Dn, give change for amount n with the least number of coins. Example D1, 25, D2, 10C, D3, 1C, n 31. So if I said that according to greedy approach, I will start with the 25. So 25, I will start with the biggest note. So biggest note is 25. So here I will give you 25. Then this one is not applicable, will be 35. So I have only 31. So 25, I will give you 1 note 25 and 6 note 1. So it will be 25 plus 6, 31. So how many coins I give you? I give you 7 coins. However, if I use another what we call dynamic programming approach, greedy solution is optimal for any amount of normal set of denomination, may not be optimal for arbitrary coin denominations. Here I can use 3 coins from 10, so it will be 30, and 1 coins from 1, so it will be 4 coins. 30 and 1, 31. So it will be 4 coins. But however, if I follow greedy approach, I will give you 25 and 6 from note 1. So banknote 1 and banknote 25 will be 1 and 6, 7. But however, if I go applying another approach like the anachrony, I will give a start not with 25, I will start with 10. So I give you 3 notes of 3 coins of 10 and 1 coin of 1. So it will be 31. Then we go to manual spanning tree. The spanning tree of a connected graph G is a connected cyclic subgraph of G that includes all of G vertices. So it is acyclic, not cyclic, acyclic. So minimum spanning tree of a weighted connected graph G, spanning tree of G, minimum total weight. So here I have tree. I want to visit all the nodes with the minimum weight. So here a spanning tree of an directed connected graph is its connected acyclic subgraph tree that contains all the vertices of the graph. If such graph has weights assigned to its edge, minimum spanning tree is a spanning tree of the smallest weight, where the weight of a tree is defined as the sum of the weights on all its edge. The minimum spanning tree problem is the problem for finding minimum spanning tree for given weighted connected graph. So here I have this graph. So from A to B, weight 1, from A to 2, from A to C 5, from C to D 3. So if I want to visit all the nodes, here if I say here A1, A2, AD, AC, it will be 1, 2, 3, 6. If I use another route, AB, A5, AC, C3D, it will be 1 plus 5, 6 plus 3, 9. If I use AD, B, D, C, AC, AD, AB, so 1, 2, 3, 5, it will be 8. So what is the best one is number 1, because it gives me only 6. Here it will give me 9, here it will be 8. So there is what we call algorithm to find the minimum spanning tree. We have Kruskal and prime. Prime is consistent. Here I start with any vertex, and here consisting of one vertex and grow 3 on vertex at the time to produce MST through a series of spanning tree, subtree T1 to Tn. On each iteration, construct Ti plus 1 from Ti by adding vertex node in the Ti that is closest to those already in Ti. This is a greedy step. Stop when all vertices are included. So this is the graph. We have here A, B, D, 4, and this is the weight of the graph. So from A to D1, from A to B4, from D to G6, here all the nodes and the weighted nodes. So I start with any node. Let's start with A. So I will check that A to B is 4 and A to D is 1. So I will select A to D. If I start with A, so I have AB and AD. We find that AD is minimum, so I will select AD. Now, from A, what is the lines connected to the here? So if I say here A4, DB4, also D6 and DB. So here 4, here 4, here 5, here 6. So what is here from this node? What is the line is coming from? So it is coming here A4 and here from D 5 and 6 and 4. So I can select D4 or AB. Let us select AB because here I say. So I selected here AD, AB, and D. Now I try to find another what we call the graph, how to select. So AD, A4 now from B. What is the lines coming? 4 and 10. 4 and 10. So here, if I will ignore this one, B4D, because it will be cycle. I don't want it to be cycle. If I select 4, it will be here cycle. So I will ignore this 4. So B10, and from D, what is the lines coming from? D is 5 and 6. So what is the minimum? 4, 10, 5, 6 is 4. So I will select C. Now from C, how many lines begin? 2, 1, and B is 10, and D is 5, 6. So what is here the minimum? Is CF1. So I will select CF1. Now, what is the lines coming from C2, from F3, 5, from B, 10, 5, 6. What is here the minimum? From 2, 1, 10, 5, 6 is 2. So I select this one, E. Now, from E I have 2. I have here F3, F I have 5, and here 10, 5, 6. So what is the minimum? Is AG2. Okay, now here J to F 3, but it will be cycle, so I will ignore 3. I will go here G to I1, G to I3, G to 4, 4, B here is 10, and 5 and 6. So here I can see that G to I is minimum. So I will select GI. Now from I, how many lines comes from I? 3. From G comes 4. From B, 10, 5, 6. So what is the minimum here? Is 3. So I will select J. Now from J, how many lines? If I make this line, it will be cycle. So I will ignore this one now. JB, it will be cycle because it will be like this cycle. So ignore this one. So here JD6, JH2, and here 5, 6. So what is the minimum here? Is H. Now I visited all the nodes, so I will stop here. So I will just redraw this one using only the lines that I selected, the weight that I selected. Here A, D, 4, 4, 2, 1, 2, 3, 3, 2. So this one, this is the tree, that the minimum spanning tree that I need to have it in my, to solve the spanning tree using prime. Then we move to the adjacency matrix. So if I have 4 points, I will have, and directed, I'll have n power 2 divided by 2. Directly, I have n power 2. Look at this graph. 0 is connected with 1, 2, 3. 1 is connected with 0, 3, 2. 3 is connected with 3, 1, 0. So if I go here, 0 is 0. The weight from 0, I don't have connection from 0 to 0. 0 is 0. 0 1 1 is 0. 2 2 is 0. 3 3 is 0. But here I have connection between 0 and 1. Yes. So I will make it 1. For 0 2, yes, I have connection 2. 0 3, I have connection. Yes. Here I will make 1, means true. Here I have connection. Yes, from 1 to 0. 1 to 1, there is no connection 1 to 1. So 1 to 2, I have a connection. 1 to 3, I have connection. And this is the rest. 1 1 1 from 2, I have 0, 1, 2, and they have also from 3, 1, 2, 0. So here from level 3 is have 1, 2, 3, 0. So here the gravity here. If I have directed graph, so undirected graph in 2 power 2, directed graph in power 2. So how much in power 2? Because I have 4 items. So 4 by 2 is 16. If I here calculate this number, I have 1, 2, 3, 4, 1, 2, 3, 4. So 4 by 4 is 16. So here I have n power 2, 16. Here n power 2 divided by, this is directed, n power 2 directed, this is directed, n power 2 is directed, n 2 power 2 divided by 2 is undirected. So this is undirected n 2 power 2. So here, if I say from 0 to 0, this is the 0, 0, there is no connection, 0, 0, 1, 1, and 2, 2. Okay. From 0 to 1, yes, I have. From 0 to 2, no, I don't have. 1 to 0, yes, I have. 1 to 1, there is no connection. 1 to 2, yes, I have. Okay. From 2, what is the connection here? Oh, nothing. So I will be 0, 0, 0. This is because it is directed graph. So here I have to have this one is not applicable because here will be 0, 0, 0 because there is no line connected with 0 and 2. Okay, now here if I have this graph, okay, for prime cannot solve graph like this. Should be connected. This one is like having two parts of tree. Okay, but as prime cannot solve this graph, but for Kruskal we can solve. So here I have 0, so 0, 0, 0, 0, 0, so this diameter. So here it will be zeros because I don't have connection between 0 and 0. 1 and 1 I don't have connection. So it will be 0, 0, 0, 0, 0, 0 from until 7. Now from 0 to 1 I have a connection 1. From 0 to 2 is I have connection 1. The rest is 0, 0, 0. I don't have connection from 0 to 4, 0 to 5, 0 to 6, I don't have connection. So it will be all zeros. From 1, yes, I have connection to 0. 1 to 1 is 0. 1 to 2, there is no connection. 1 to 3, connection. So here, and the rest is 0. From 2 to 0, yes, I have connection. From 2 to 1, no, I don't have connection. From 2 to 3, yes, I have connection. Okay? And the rest is 0. From 3, I have connection to 1 and 2. 0, there is no connection. So here 0 is connection, 1 and 2, 0. The rest is 0. Now from what you call here, now 0, 1, 2, 3. For node 3, I already solved. For node 4, 4 is connected only to 5. So here 4 connected 5, and rest is 0. And there is no connection between 0, 1, 2, 3. So it will be here all zeros except here for 4 to 5. For 5, so 5, there is no connection between 5, 0, 5, 1, 5, 2, and 3. So it will be 0, 0, 0, 0. I have only connection between 4 and 6. So for 5, for node 5, I have connection between 4 and 6. And the rest is 0. For the node 6, I have 5 and 7. 5 and 7. For node 7, only with 6. I have connection with 6. So this is the graph using adjacency matrix. So if example of this linked list, so here 0, 1, 2, 3, here all have connection. For this one, if I use the list, so here 0 to 1, this one graph. 0 to 1, yes, only 0 to 1. For 1, I have 1 to 0 and 1 to 2. So I have 0 and 2. For node 3, there is no connection because it comes from 1 to 2. There is no coming from 2 to 1 or 2 to 0. So this will be null. For this one, I have a 0 and I have 2. For this one, I have 0, I have 1 and 2. For node 1, I have 0 and 3. For node 2, I have 0 and 3. For node 3, I have 1 and 2. For node 4, 5. For node 5, 4 and 6. For node 6 is 7, 5 and 7. For node 7 is 6. This is the linked graph. So now go to what about Prime's algorithm. Proof by induction that this construction actually yields median spanning tree needs priority queue for locating closest finger vertex. Efficiency O n power 2 for weight matrix representation of graph and array implementation of priority queue. O m log n for adjacency list presentation of graph with the m vertices and m edges main heap implementation of priority queue. Okay, so here we have here n o n power 2 matrix with the grapher and any implementation of priority queue. O m log n for adjacency list representation of graph with 8 vertices and m edges and min heap. So we have something called min heap. Min heap is give me direct the minimum value, No need to calculate or compare. Only they give me directly the minimum value. Okay. So we go to Kruskal algorithm. What is Kruskal algorithm? He said same graph that I have example. I just get the connections. Here, this is the connection between A, B4 and BD4, AD1. So I will write all the edges. I write all the edges from A to B4, from B to C4, from A to D1, all the edges that I have. And then I sort them non-decreasing way, means ascending way. So here I will start with AB1, AD1 and CF1. Okay, I will start this one, AD and CF, because they will be the minimum. I will start with this and then the decreasing order. So with 1 and 1, then 2, I have 1 CE, AG, HG, HD. So I have 3 lines. So here, this is sort edges. In reality, they can place in a priority queue, not sorted, but sorting them makes the algorithm easier to visualize. So here, so after sorting the links between the nodes, now here I start with the selecting the edge. So AD, I select AD, then I select CF, then CE, EG, for EG, okay, FG, no, I have 2 also. Is there is I have 2, HJ2. So now I start selecting edges according to the weight value. So here I start with 1, 1, then 2, 2, then 2, and now the 3, ascending order, FG3. FG3, if I select this, will be cycle here. So I will ignore this one. Ignore it. Now GI. GI4, GI3, GI3. So GI3 is okay, boleh. Now IJ. Where is I? IJ, yes, boleh. AB, 4. Okay, boleh. BD4. BD4, if I select this one, it will be here cycle. So I will ignore it. Then BC. BC4, yes, I selected. GJ. Where is GJ? GJ. GJ will be cycle. So I will ignore it. Okay, if I notice that I have already visited all the nodes, and if I see here the rest of the node, the rest of the links will make a cycle. So GJ will be cycle. GJ. Yes, it will be cycle here. FI, it will be cycle here. DH, DH, it will be cycle long, very long cycle here. DJ, so it will be also cycle. DJ will be cycle. BJ also it will be cycle. That's why I ignore of them. So here the solution is this. This is the minimum spanning tree. 1, 4, 4, 2, 1, and the rest, the red one is ignored. The red one here, like this, the red nodes are ignored. We don't use it for the spanning tree. No, notes about Kruskal algorithm. Algorithm looks easier than primes, but is harder to implement, checking for cycles. Cycle checking a cycle is created if the added edge connects vertices in the same connected component. Okay, union find algorithms. Okay, this one from the book. You can see here union find algorithms in chapter 9, part 2. This is for the here. I have examples. We did some examples here. So here prime, if I have graph like this, find MST using prime. So here I will start with A. Where is the mouse? I start with A. Then from A is coming 2 and 4. So minimum is 2, I will select 2. This is using prime. Exercise using prime. So here I use 2. So here I have A and B. From A and B, we have 3 coming and 4 and 4. So I will select 3. So B, C, 3. Now from B is 4, from C 1, from D 4. So I will select CD because the minimum D. So I will select CD. This is the prime, not Kruskal prime. So here D. Then from D I have what? 3. And I have here C 2. And here I have 3. And here I have 4. So what is the minimum? Is 2. CE. So I will select CE. D3, DE. If I select DE, it will be what? Cycle. So I will ignore D3. So here DG3. Okay, from here AG4, from EF5. So minimum is DG. So I select DG. Now here from G I have 2. Okay. Here I have from G only 2. and from E5, from G2, from E5. So here I have only 2 is minimum, so I will select this one too. So the lines that I connected, choose it here. This one A, B, 3, C, D, here E, 3, 2. So this is the minimum spanning tree. Minimum spanning tree using prime. Okay, now I will use crosscal. So this is the lines A, B, A, G, B3, B, D, C, D, C, E. So here I have, this is the links with the weights. Now I sorted them in ascending order. Each one I send them in ascending order. The links. Then I start CD1. I select CD1. Where is CD? I select first CD. I have to redraw all the lines. Why I have it like this? I will draw it again. I will use Cruscal, but let me go here. Where is the answer? This is the answer, but I want to see how I answer this one. This is the graph. So first I have AD1. I have what is here? CD. First I start with CD. CD. Let me use green color. CD. Okay, now I select C and D. Then AB, because these two. Okay, 1 and 2. Then here, what is after that? CE, CE. Then CE, FG, FG. in non-decreasing order and ignore if there is cycle. Okay, FG, BC, BC. Okay, now I notice that BC. Then if I select DE, DE, it will be what we call DE. It will be cycle. DE cycle will be ignored. DG, DG, it will be also cycle. This cycle. Okay, so I'll ignore it. DG, AG, AG, it will be cycle. BD, BD, it will be also cycle. EF, it will be also cycle. EF, it will be uh, EF. Okay. Here I select the DG. DG, it will be cycle? No. DG, it will not be cycle. Okay. Now I stop because I already connected this one. If I select F DG3, 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 okay, select DG. AG, no, BD4, EF, also it will be cycle. If I select now this one, it will be cycle. So this is the solution. A, B, C here. So this one, the link that I don't need, I will erase it. So this one, no need. This one, no need. This one, no need. This one, no need. So look, compare between this and this figure. It is the same, okay? A, B, 3, A, 2. So this one the same. So this is the answer using Cruxal algorithm. Okay? Now we go continue. Any questions so far? Any questions so far?
No.
It's okay. It's clear. Am I right? It's easy, this one. Okay. Now we cover part 2 of greedy approach. Okay. Before that, I give you 5 minutes break. 5 minutes break, and then we continue. Okay? 5 minutes break, then we continue. So before I continue, please don't forget to make the attendance. So for the Dijkstra algorithm, I think already have exercise on this one. The Dijkstra algorithm. So I have this one, A, B, A, D, B, E, E, D, E, F, E, C, okay? This is the Dijkstra algorithm. So I have these nodes. This one undirected graph, not directed graph, undirected graph. So here, what is the problem? I want to find the sorted path. So here, I mark all the nodes are as unvisited first. Then start with the node that I will start. So then I make the table from A to A. It will be the distance is 0, and what is the next node. So the current node, I make a table, node and short distance and previous node. So A, what is the shortest distance is 0. I start like this. A, what is the shortest distance? Because I start with A, so A with A is 0. So previous node is A, so 0. So I'll start here with the A. So I'll make all the nodes infinity. Now I compare between the nodes. So for the current node, calculate the distance or unvisited neighbors, update the shortest distance if new distance is shorter than all distance. So from A to B is 2. So here B shortest distance is 2. What is previous node? A. So here I will update this one, B to A. Okay, B to A. Now from A to D. From A to D, the distance is 8, so less than infinity. So I was filling all the nodes are the shortest distance is infinity unless the starter point. So 8. 8 less than infinity, yes. So I'll be 8 and the previous node A. So now I have 2, 8. Now, so I mark this one as a visited. Now, what is the list here from B and D? What is the minimum from B and D? Is B. So here I select B. So B to D, it will cost 2 plus 5, 7. B to D, it will cost 2 plus 5, 7. 7, here I saw D. D, here 8. 7 is less than D? Yes. Less than 8? Yes. So I will replace here 7 and I make the previous node B. Okay? Previous node will be 7. Okay? Now here from B to E, 2 plus 2, this one 2 plus 6, the weight plus 2, 8. 8 for E is less than infinity, so I replace here 8 and I will make here E, the previous node is B. Now here I mark the B as visited. Now I go to D. Okay, B, D. D. D I have here, I have here 3, okay, 3 to E and 2 to F. But from D start with 7. So 7 to E is 10. 7 plus 3, 10. 10 is less than, where is E? 10 is less than 8? No. So I will leave it here. Here, 7 plus 2, 9. 9 to F, yes, less. So I will make here 9. I will make here 9. And here, previous node is D. So 7 plus 3, 7 plus 2. So here 7 will keep it. Because here and 8 here, 10. 8 here, 8 is less than 10. So here it will be 8. And here F 7.9. Now I will replace here 9. I will put here D. I already sent you this file. 9 here D. Now I visit A, B, D. Now I go to E. E going to 9 and going to C and F. So what is E? E starting with 8. 8 plus 9 to C, 17. So here E, okay, E to 9, 17. So means 8 plus 9, 17. So here to C, 17, and the previous node is E. And here E to F, E to F, 8 plus 1, 9. 9, and here 9, same. So I will keep it. 8 plus 1, 9, and 8 plus 9, 17. So here I will place this 17. I will keep this one now. Now I go E visited. Now F. F, I have to see how much F? 9. 9 plus 3, 12. So if I go here, see what is the previous node of C? 17. So 12 is less than 17. I will replace here C with 12, and E, I remove E, I will put F. So here 9 plus 3, 17, I will put F. Now C is visited and all here are visited. Now I make here from starting from the endpoint C. What is the previous node? F. So I make C F. After F, what is F? Here F. What is before F? D. C F D. Then D. What is before D? B. So C F D B. Then B. What is A? So here will be C F D B A. C F D B. Here should be. Let me copy this one. Here B should be C F D B. So red color. Need line. I'm not sure it will be insert line row. Okay. So CFDB, this one also red. CFDB A. And here B, what is before B? A. So here, okay, this is the Dijkstra algorithm. Clear? So now, so the digital group single source sorted path problem given a weighted connected graph G, find sorted path from source vertex S to each of the other vertices. The digital algorithm similar to Prime's MST algorithm with a different way of computing numerical levels among vertices not already in the tree. In the tree, it finds vertices vertex AU with the smallest sum dv plus wvu, where v is a vertex for each sorted path has been already found on preceding iterations, such as vertices for a tree. dv is the length of the shortest path from source to v. wvu is the length weight of h from v to u. This is here example. Here A, B, C, D, E, and here it says 0 and all the here infinity. So here initialize infinity. Same like the answer, but with different what we call here with different like different explanation. So here I have A to B 10. So I replace A to B 10. A to C 3. So I replace here 10 and 3. Okay. Now here I will replace B like this one. Okay. B to here 10. Here if I say 3B 3B7 3 here A C B, it will be 3 4 7 7B will be 7, and here go to B here 10 to here. So this one, I think the one that I give you is easier than this one. Okay, this one is the one that I give you is easier. So note that the scale algorithm does not work for graphs with negative weights, applicable to both undirected and directed graph. But if this negative weights, it will not work. Applicable for both undirected and directed graph. Efficiency OV2, number of vertices of graph represents by weight matrix and array implementation of priority queue. OE log V for graph represented by adjacent list and min heap implementation of priority queue. If you use a heap, means find the minimum value direct. It will take O edges, number of edges, log number of vertices. Here O vertices power 2. This is the efficiency. So how many vertices we have? Okay, we make V of 2. Here, how many edges we have? Number of edges, log number of vertices of graph represented by edges listed a minimum heap implementation of priority queue. Don't mix up the digital algorithm with prime algorithm. So we don't mix two algorithms together to find the shortest path. Okay. Now we go to something called Hoffman quotes. Hoffman quotes is an binary tree with edges labeled with zeros and ones, yields a prefix-free quotes of characters assigned to the leaves. Okay, optimal binary tree minimizing the expected weighted average length of code word can be constructed as follows. Hoffman algorithm, how it is going to use. Initialize in one node trees with alphabet characteristics and the tree weights with their frequencies. Repeat the following step n minus 1 times. Join two binary trees with smallest weights into one as left and right subtrees and make its weight equal to the sum of weights of the two trees. Mark its edges leading to left and right subtrees with 0. When I go to left, I mark with 0. When I go to right, I mark with 1. So here I have this graph, but because I'll go to the example, I have some notes. It will be helpful for you. Let us go through that notes. Hoffman. Wait. Okay. Now assume that we have this message. B, C, C, A, B, B, D, D, A, E, C, C, B, B, A, E, D, D, C, C. So how many letters we have here? Length is 20. If I count this here, 1, 2, 3, 4, 5, 6. Okay. How many the message? How many the length of message is 20? If I'm using ASCII code, each character will be represented by 8. So how much I have here? 8 multiply 20. So here, look at this one. So according to ASCII, A is represented by 65, B is represented by 66, C here, and here we have 8-bit. Binary code for representing A is 8-bit for ASCII code. So 65, this is the 8 binary code, 8-bit. So here we have 8-bit. So size of message is 8. 8 binary code for each character will be represented with E-bit. 8-bit. 8-bit. So how many characters do we have? 20. 20 multiple 8. How many do we have? 160. So to represent this one, I have 20 characters, and here each character will be represented by 8-bit. So I have 8 multiplied 20, I have 160. Now for Hoffman, it said that I can represent this message with less than this size of bits. So size of message here 160. Okay. Character, how many times character A appears here? A 1, 2, 3. B how much? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So I just make the frequency of the letters that appear here. So I have these characters A, B, C, D, E. So here I have 3, 5, 6, 4, 2. What is this? 3, 5, 6, 4, 2. This is the frequency of the characters in the message. So I said that I have message with 20 characters, and the frequency of this character is as follows: 3, 5, 6, 2, 4. So how much the total here will be? 20, 8, 14, 18, 2, 20. So this is should be the total is 20. So 3 uh, uh, 3 of 20, 5 times of 20, 6 of 20, 4 times by 20, and 220. Here I want to make a code. How many letters I have? 1, 2, 3, 4, 5. If I use 1 bit, I can represent only 2. If I use 2 bit, I can represent 4 characters. If I use 3 bit, I can represent 2 up to 3, so 8 characters. So here, because it is here 1, 2, 3, 4, 5, so I will make 3 bits. So here 0, 1, 2. Here for 2, I have present 4. For 3 bits, I can represent 8. 8 characters from 0 to 7. 0, 1, 2, 3, 4, 5, 6, 7. So from 0 to 7 means 8 characters. Assume that I make like this: 0, 0, 0 for A, 0, 0, 1 for B, 0, 1, 0 for C, 0, 1, 1 for D, 1, 0, 0 for E. Why I cannot use only 2 bits? Because 2 bits will represent only 4. That's why I use here 3. Okay? This one, until now, I didn't go through Hoffman. Still in the beginning. So here, according to this formula, how many letters I have? I have 20. Am I right? How many bits I represent here? 3. So I have 20 characters. Multiply 3 is 60. 20 multiply 3 is 60. And I have only 5 characters: A, B, C, D, E. So I represent using ASCII 8. So here 8 multiply for the characters, 5 multiply 8, and here for representing the codes, 5 multiply 3 for the code. So how much I have? I have 5 multiply 8 is 40, and 5 multiply 3. So how many 3? 1, 2, 3, 1, 2, 3, 1, 2, 3. How many? 5 multiply 3, 15. So how much total? 40 plus 50, 55. The message is, as we said here, 60. Am I right? Because we have here, we minimize the letters to 5 characters, multiply here 20 message, 20 characters multiply 3, 20 characters multiply 3, 60. 20 multiply 3, 60. Okay, 60 plus 40 plus 15. So 40 message is 60. Why 60? Because I have 20 message. I use code 3. So 20 multiply 3 is 60. And this 5 bits for the ASCII is 40. And for the code is 5 multiply 3 is 15. So 55 plus 60 is 115. So rather than use 160 bit to represent, I will use 115. I may manage to use 115 bits to represent this message. Previously, how much I used? 160. Now, after this kind of manipulation, I use 115. Now I will go to Hoffman. This is the idea that I give you, that how can I represent the message. So here I decrease the message. So I represent only using 115 bits. I go to Hoffman code. Same here, Hoffman code, messages, same message. Now same table, A, how much it appear, 3, 5, 6, 4, 2. Now I represent this according to the count from the ascending order or non-decreasing order, ascending order. So E is 2, A is 3, 4, 5, 6. This is now the Hoffman code. Okay, now 2, 3, 4, 5, 6. After that, so here. Now I try to find the minimum between these two, between each two nodes. Okay, 2, 3, 2, 3 is 5. So here 2 and 3. What is the minimum nodes as connected? 2 and 3 is 5. Here 3, 4, 7, 4, 5 will be 9, 5, 6 will be 11. So here 2, 3, 5. Now, if I connect 4 with 5, will be 9. If I connect 4 with this 5, will be 9. So here I can connect this one or connect these two here. This part with this part will give me 9. If I connect 4 with 5, it will give me 9. Okay? Now, five and 6, how much? 11. 5 and 6, 11. So now, neighbors node, I'll give here neighbor and connect it and try to find the minimum. So 2, 3, 5. 4, 5, 9, maybe here 9 same, or 4, 5, 9 here. So here 5 and 6, 11. Now, if I say 11 and 9 will be 20. 11 and 9, how much? 20. Now, according to Kruskal, if I go left, I make 0. If I go right, I make 1 to the edge. Let me go here. When I go left, I mark this with 0. 0, 0, 0. When I go right, I mark with what? 1, 1. I go left, 0. I go right, 1. I go right, 1. Okay, so how can I make these notes? connected. Here I make here the nodes according to here minimum nodes, minimum value 2 3 5. If I say 3 4 7 4 5 9 5 6 11, so I start with this one 5. Now 4 5 9, I can give here also 9, or here 5 with 4 with 5 9. Okay, see, 5 and 6 11. Now 11 with 9 20. Now I go 0, I go here right 1. When I go here to the left, I mark with the label with the 0. When I go here, I mark 1. Now look here what I'm going to see. Here I have the code 0 0 0 will be the code of E. 0 0 0 is the code of E. Zero zero one is the code of A. One zero is the code of B. Only 1 0 code of B. One is the code of C. 1 is the code of C. What is D? D01. D01. Now I make how much I have here? 3 bits. Here 2 bits. Here 2 bits. Here 2 bits. Here 3 bits. How much the total? 3, 5, 7, 9, 3, 12. So 12 bits. So here 3 multiply 3, 9. 5 multiply 10, 10. I mean it's 2 bit. Multiply 5, 10. 6 multiply 2 bit, 12. 4 multiply 2 bit, 8. 2 multiply 3 bit, 6. So how much the code is? 45. If I manage here, 9 plus 10 plus 12 plus 8 plus 6 is 45. The code, how much the code? 12 bit. The code is 12 bit. 3 multiply 3, 9. 5 multiply 2, 10. 6 multiply 2, here 2 bit. 2 bit. Here 3 bit. How much the frequency? 3 times. 3 multiply 3, 9. 5 multiply 2, 10. 6 multiply 2, 12. 4 multiply 2, 8. Here. So the code is 12 bit, and the message here, the message is here 45 bit. So here 12 multiply 45 is how much? How much? Here message is 45. Message is 45. Code is 12. How many bits I have? 5 letters. ASCII code 5 multiply 8, 40. 40, and the coding here is 12. Coding is 12. So it will be 52. 52 plus 45 is 97. So this is the 97. So when I used last time this code, I managed to use it 115. Am I right? Before I used Hoffman, Before I used Hoffman. Hoffman, I make the message using 115. Without any doing anything, I use 160 bit. Now I use 115. Here now I use 97. Am I right? 97. 45 plus 52. Codes 12 plus 40, the ASCII code of the 5 letters, 25 plus the message 45. So 45 plus 55 is 97. So here, sigma DI the code 3 multiply 2 plus 3 multiply 3 plus 2 multiply 4, the frequency. Plus 2 multiply 5 plus 2, here DI the code. So it will be 45 as written up. For decoding, so now this is coding. For decoding, if I have like this, B, C, C, D, B, okay, B, how much B? B is 1 0. B is 1 0. Okay, now I'm writing the code. B, C, C, D. B 1 0. C, what is C? 1 1 1 1. A is 0 0 1. Here 1 0. So here for decoding, I'm writing here the representation of this one. So here 1 0 is B, C is 1 1, C 1 1, D, what is D? D is 0 1, A is 0 0 1, okay, C is C is 1 1 1 1. So this is the message and how we are making here decoding. So here if I want to make this replacement, here I have this one. Okay, now that's all for Hoffman. So if I have BCCD, so what I'll have here? B 1 0 1 1 1 1, and here how much? D? D is 0 1. Okay. So this is the message and this is the code that I'm going to send. Clear so far? So when I start, if I have 1 0, 1 0, it is B. 1 1, it is C. 1 1, it is C. 0 0 1, 0 0 1, A. Okay. Now here, this is the Hoffman code. Let's go to the example that we have in the here. I will send you this one. Don't worry. I will send you this one. But let us go to the example here. Here characters I have A, B, C, D. What is the characters that I have? A, B, C, D. So this is the frequency. How many times it appears? So here 0.5, 0.1, 0.2, 0.2, 0.15, 0.35. Now I just arrange them in ascending order. So what is the minimum here? 1. B is 0, 1. Then this is the frequency. B 0, 1. Then underscore 0.15. Then C and D 0.2, 0.2. Then A 0.35. Now, as Hoffman, what he said, Hoffman, try to find the minimum points. So here, let me here. I want to make here this one. This one is same, but here I want here I will merge. I mean two notes, 0.15 and 0.1. This is the two minimum. So it will be 0.25. Okay. Okay. Let me here draw this one. Snipping. Hoffman is very easy. So can you see my screen?
Yes.
Okay, let me close this one. Okay, now zero point 0.15, how much? The two minimum nodes. So here will be 0.25. Okay, now okay, now this one 0.25. Okay, now here also look at this here. I can make here 0.2 and 0.2 each nodes here. How much will be? 0.2 and 0. If I make 0.2 and here 0.5, it will be 0.25 45. It will be 0.45. Am I right? 0.2, 0.45, 0.3 with this one, it will be 0. 25, 60. So I will make here this one, these 2 points. Thus, I want to make just combine the two nodes that minimum value. Here 25, if 25 with 2, 45. Okay. 2 with 2, okay, 40. So I will make 40 here. So 0.4. Now, 0.25, 0.4, how much? 0. Okay, look here. 0.25 and 0.4. How much will be? So total, how much total it should be? This is the total. Let me run the calc. The frequency should be the total, the frequency. Calc. So what is the total? 0.35 plus 0.1 plus 0.2 plus 0.2 plus 0.15. How much equal? 1. Okay. Now, okay. So here 0.4, now 0.35 and 0.25 will be how much? 60. Okay, we'll go back here. 0.25 and 0.24 will be 0.26. But however, 0.35 and 0.25, how much will be? 60. Am I right? That's why I give you like this, 60. I will redraw like this here. New 60. So here, this one. So it will be like this. Zero 0.4, it better like this. So here, I merge this one. So now here, I have this one, 0.6 and 0.4. How much 0.6 and 0.4 is 1. Now look here. This is the tree. Now when I go left, I label 0. When I go right, 1. So here I go left, 0, 0. This is the tree. This is the tree. When I go left, I mark 0. When I go right, I mark 1. So here 0, 0, 1. So here I mark here 0 and 4 like this. This one, I make it like this. 0, 4, here I put it here. Okay, I will put it here. Okay, 0, 4, like this. 0, 4, here. So here, like this. 0, 4, 0, 6. 0 0.4, 0 0.6. So here, when I go to the left, 0. When I go right, 1. Go left, go right, 1, 1. Go left, 0, 0. Go right, 1. Now, what is the code of C? 0, 0. What is the code of D? 0, 1. What is the code of B? 1, 0, 0. What is the code of A? 1, 1. What is the code of underscore? 1, 0, 1. So here, look here. A, what is A? 1, 1. B, 1, 0, 0. C, what is C? 0, 0. D, 1. D, D0, 1. D0, 1. Underscore 1, 0, 1. Okay, this is the same like I give you the example, but in my example, I think it's more clear than this one. Okay, now here I calculate the average bits per character, 2.25 for fixed length encoding 3. Okay, compression ratio 3 minus 2.25 divide by 3 multiply 100% percent. So I compress this one 25%. So I compress this 25. So here I have to compress the 1. So if I want to see for my example, where is my example here? Here, for before I use Hoffman, for the one that I use here, it was how much? Percentage calculator. Okay. How much it was? I think here, increase. Percentage difference calculator. This one was not this one calculator. I think this one. Okay. Increase, decrease. It was 160. In here, I use 115. So how much? So I compressed 28%. Okay, now here, how much it was? 160. Then I message the message. I decrease it to 97. Am I right? 97. 115 first time. Then using Hoffman, I decrease it to using Hoffman to 97. So where is the calculator? To 97. So how much I decrease it? 39%. from 160 to 97. So the compression is 39. So I decrease this one 39%. Okay, this is the Hoffman. Again, we'll do exercise during the labs, don't worry. This is the Hoffman, and it is easy to hire. I will send you this slides and also this note for Hoffman using this code. Okay, clear so far? Clear so far?
Yes.
So here, because this one I have here. Okay, make it here, this one. Control C, Control V, like this. So I move this one here. Then I connect this one with this point. Then connect here. With this. Okay. Okay. So don't forget to make the attendance. This is all of for today. So thank you very much, and don't forget to make the attendance. We have exercises in the lab. Don't worry, and we'll go through it Hoffman again. We will go through Hoffman again. Okay. So hopefully it is you got what I have for today. Thank you very much, and Assalamu alaikum wa rahmatullahi wa barakatuh. Don't forget to make the attendance. Any questions so far?
Doctor,
Yes.
I want to ask, when is the deadline for our assignment and group project submission?
Okay, I will let you know. Inshallah, I will let you know.
Next week. You will tell us next week.
Yeah, next week I will inform you what is the time for the group assignment and for the project presentation. Okay.
All right. Thank you, Doctor.
Okay, Ashraf.
Thank you, Doctor.
Okay, welcome. Okay, welcome.
Thank you, Doctor. Assalamu alaikum.
Alaikum assalam wa rahmatullahi wa barakatuh.